Hi friends, it's Ben again. Uh, this is a video for the differential equations class. We're looking at using the separation of variables technique to actually solve some partial differential equations. Okay, so the essential notion of the separation of variables technique is that you have a partial differential equation that looks like it's linear homogeneous. Okay, so the terms will seem a little bit off on this because you got to think about a derivative with respect to more than one variable here, right? But it's going to look like it's something that's linear and might be homogeneous, and you make this guess. I think it was probably a guess the first time somebody looked at it, but there's stuff to back it up. Okay, you make a guess that you can separate your function into functions, factor it into functions of one variable at a time. So often in the examples we're using, we're going to use u to be the name of the function we're solving for. And so you make this guess that maybe you can factor u of xt into a function, say v of x, and another function w of t. Seems like that's kind of an out there thing, but as it turns out, you can find solutions either that follow this, or by summing up a bunch of solutions that that follow that sort of guess, you can get something which is as close an approximation as you need. A little weird, but in any case, that's what we're tackling here. So let me pull up an example, and the examples are going to be a little bit burly. So let's see whether it'll work. And when I told it I wanted to do screen mirroring, the Mac was the one that was trying to choke, and so the iPad is okay. All right, so separation of variables, yay. So here is our main theorem that we need to think about here. So we're going to look at a particular differential equation, this one with the alpha squared u sub xx equals u sub t. So derivative, second derivative with respect to x, and one derivative with respect to t. And the theorem is that there's going to be some constant value lambda, so that v double prime plus lambda v is 0, and w prime plus alpha squared lambda w is equal to 0. So in other words, that presupposition that we could separate it into those two pieces, we're going to be able to find two pieces that that works for, and those two pieces are going to have certain properties. This property here is going to give you solutions that are sines and cosines. This property here is going to give you solutions that are exponentials. Okay. Now, as a matter of fact, I forgot to put a little detail on here. And what I needed to say is that the lambda we're going to get on this is going to be greater than 0. Okay. All right. So taking a look at this, we're going to go ahead and write our u to be v times w. Just going to assume that you can follow that the v is the function of x and w is the function of t as we go along here. So our u sub xx is going to be v double prime w. W, remember, is just a constant so far as x's are concerned. And then the u sub t is going to be v times w prime, because remember, v is constant so far as those t's are concerned, right? So if we just plug back into the equation here, then we end up getting this alpha squared v double prime w equals vw prime. Then by just undoing some cross multiplication, we get this v double prime over v by itself, and we get this w prime over alpha squared w. You could put the alpha with either piece but it's a lot more convenient to put it with the W's than it is to put it with the V's. So here we're going to say that that is equal to some negative lambda. Later on, we'll see why that lambda had to be negative, okay, or why we needed a negative with that lambda. But for right now, just kind of play along with it that we've got that negative lambda. So the thing is, we have separated this out. This is a function of x alone. When you change t, it does not change. This is a function of t alone. When you change x, it does not change. Therefore, there has to be some constant that both of these are equal to. That's kind of a wacky little bit of reasoning there. It took me a little while to come to terms with that myself. So if we write that equation out like that, and write that equation out like that, we can actually solve those. We know the general solution from having done these previously, although that general solution needs to actually have the right variable in it. Silly head. It's supposed to have an x in here. All right. And then, yeah, the other portion here, that's just a first order linear differential equation. It's got a constant coefficient, so just bam. You'll have some c, don't know what the c will be, times e to the minus lambda, minus alpha squared lambda, and then times t. So, all right, that's the bit that we need there. Then the other bit has a term in it you are probably not familiar with. Well, okay, you probably use it in the English words sort of meaning, but for non-trivial solutions in a differential equations class, we are referring to solutions that are not just zero. Zero is a solution to a lot of differential equations. You know, if they're homogeneous, it's always going to be a solution, but it's not interesting. It's not useful. So that's the reason why we say non-trivial solutions, so non-zero solutions to this equation, if they have the value at both ends being zero, the only possibility is that we've got sine n pi x over L, and I should probably put a little note in here for some n, which is a positive integer. Okay. All right. So we're going to start out with this, and we're going to say, all right, I've got my solution to that differential equation. Boom, it's this. We put the a and b in there to let it be general, and then we go in with these values at the endpoints. Now, this is a boundary value problem. We haven't really worked with boundary value problems before, but they are the meat and potatoes for a partial differential equations problem. So we're plugging in one in there, and we know that sine of 0 is 0, so, and cosine of 0 is 1. So consequently, the a value has to be 0. So that means that our v is just b times the sine root n. I said root n. Man, that is yet another error. I'd like to call them errors in typing, but I wasn't typing. So a little error there. But we've got to have a b sine square root lambda times x. Now, if the b is also 0, then our solution is trivial, right? Because if both a and b are 0, then v is 0. The solution isn't what we want. So then we look at the other end here. We want v of L to also be 0. So you go ahead and say the b is sine times a radical lambda L. If the b is not 0, then the sine had to be 0. When is a sine 0? Well, sine can only be 0 if it is an integer multiple of pi. So once you know that it's an integer multiple of pi, then we go ahead and solve for our square root lambda and have that n pi over L. And I should also write in here that the lambda then is going to be n squared pi squared over L squared. For the use that we're putting it to, we don't need to have solved for the lambda, but in the previous page, we saw n squared pi squared t over L squared pop up, and it popped up exactly from this right here. So we've got to actually coordinate those two problems together at the same time to get our solution, right? So we are going to do a heat diffusion equation, and the setup on these heat diffusion equations is that, oh, and naturally I never got around to writing out what the yeah, I never wrote down the actual equation of what we need to look at here. So we need to be looking at alpha squared u sub xx is equal to u sub t. But we go ahead and say in the problem statement here, alpha is going to be 1. So consequently, I'm going to just plug in a 1 there, have u sub xx is equal to the u sub t, okay? And the initial distribution on the interval from 0 to 40 is going to be this right here. Maybe I should go ahead and draw that in with the actual arrow. Okay, so, or for that matter, I could make this look a little bit better by putting the picture up close to the equation. There we go. All right. So over that interval 0 to 40, it's just going to make this kind of a tent shape out of it, right? You can go ahead and write that equation using absolute values, and I'm going to explain to you why you don't want to do that here in just a minute, but it's yeah, it's not really all that big of a deal, but it's something that we'll need to have. All right, so we have our u sub xx there is equal to the u sub t. We know that it's one of these kinds of equations. And then this initial distribution that we have to give. If you're looking at what the problem is physically, we have some sort of a thin rod that has a heat profile on it. In this particular case, the heat is very high in the middle of it, but both ends of it are relatively cold. So that means that if you look at what's really going to happen physically, the heat is going to flow out of that middle, and eventually the entire heat of the bar is going to come down to some average so that it's all kind of uniform, okay? And that is, in fact, what these equations are set up to do. They're supposed to have the heat flowing away from the places where there's high heat and toward places where there's low heat. So the solution form that we had is written on your paper, which hopefully I will have uploaded by the time that you see this. And that solution requires you to calculate these values C sub n. The formula that you have is going to be 2 over L, and then the integral across whatever your interval is. Now notice it doesn't have to be a symmetric interval, okay? Fourier series that we were doing before, that was an important part of it. But here it's just being a little bit more general. In retrospect, I kind of wish I'd done things across 0 to 2 pi so as not to cause that sort of confusion here. But you're just going to take your f of x, multiply it by n times pi times your x, and then divide by 40. So whatever the length of your interval was, that goes down here, okay? So then we have to go ahead and integrate that. So for me doing the integral there, I went ahead and broke it apart into two pieces. And in doing that, I don't want to integrate it. Gosh, how do I avoid integrating something? How do y'all avoid integrating something? Why, look, it's our good friend Symbolab. So for that Symbolab, I'm just taking the f of t. Well, I use t here instead of x, but that shouldn't really matter. I will change it just because I'm a little bit OCD here, but it is worth noting for you all because at the end, you're going to have integrated out all of the variable. It doesn't really matter whether you use an X or a T or whatever, okay? So I hit go and it does the integrating and it goes chug, 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 okay? And the answer it comes down to, can I zoom in now? Yeah. It comes down to, come on. Sound like Joe Biden there. Come on. Oh. Except I'm going to use more foul language than he does. All right. I am not going to highlight this, but hopefully y'all can see what I'm pointing towards. And please ignore the ad down below. It has 160, then the sine of n pi over 2, and then divided by pi squared n squared. All right. So that sine of n pi over 2, you have to think about what that does. If you think about the unit circle and you start at n equals 0, then you're going to, then you're going to rotate around as you increase the n values. And at n equals 0, you get 0. But at n equals 1, you get 1, and then 0, and then minus 1, 0, plus 1, 0, minus 1, and so forth. So it only gets you non-zero results at the odd multiples. I got sick of trying to write the program with odd and even stuff. I just couldn't make it work the way I wanted it to. So when I was writing code for this, I just said sine of n pi over 2. I don't like it because there's these zero terms that get knocked out that I'm making the computer do extra work for, but yeah, it gets tiring otherwise. So in any case, then that means we can pop back to what we've got on the iPad and see that little note that I was making there. So, okay, yeah. So see that little note that I was making there that for even values of n, we're going to get an integer multiple of pi, and therefore the terms drop out. But if we come back over here to the next page, we're going to have a summation, and I just put n greater than 0. I don't bother to put anything other than that. Yeah, if you notice, you're not going to evaluate this where n is equal to 0 for obvious reasons. And so this is just kind of a shorthand I like to use. But here is that c sub n term that we figured out, the 160 sine of n pi over 2, and then divide it by the n squared pi squared. And then I said e to the minus n squared pi squared t divided by 40 squared 1600. So that's kind of a handful there. And then sine of n pi x, all right? And then I went ahead and used something. I went ahead and used Colab to produce a graph of this. And as I'm looking at the graph, I see there's a small problem with it. And see if y'all spot what it is. The graph that we were drawing needed to go from 0 up to 20. This one goes from 10 to 30. And I did not spot that until just this minute. We'll try to take a look at some code here. Okay, so I'm going to show you what I've done with it, and hopefully that'll help you all see what you can do. So notice though that when the t value is equal to 0, and I draw this with this being the x-axis down here, then I get that initial shape that's kind of that tent shape that we referred to earlier. Then as you allow the values of t in here to get larger, they will take that tent shape and they will slowly make it more and more gentle until it eventually gets flattened down here to this, where I said the u turns out to be equal to 10 on it. So I wonder if I can fix that later. We'll see. Okay. All right. So coding how to get that to work out. I'm going to pull that up here and let y'all see. So this, I just took the Fourier plotting stuff that we had yesterday. Aha, I see what went wrong with it. Okay. So the thing that went wrong is that I had 10 in here, and either I needed to have 0 times it, or I needed to have, since I've got it down here elsewhere, or I could have done this np dot zeros like x. Okay, that's just a tricky little way to turn about doing that. So if I do that and then I reevaluate that, yeah, and then I've got this plot in this wrong place. So zeros like x. All right. Oh, it doesn't like that. What does it not like? It doesn't like zeros like. Well, np dot zeros like. Sorry to bumble around in front of y'all here, but here's that graph that I showed you, and I will totally come back and try to fix that on the notes before I send it to you. But the thing that I did with it was I came along here and I changed from talking about t to changing it to talking about x on these. And then I had a t value of 0. And then my n, I went ahead and said 100 because it took me quite a few terms to make that sharp edge look like it was pretty sharp. You don't have to do that many terms, like 10 is probably good enough for a starter. Then I have the initial condition there. This is not the initial condition, but I have the starting value there for the s of being zeros. And then when I come down here to do something with it later on, I can just add terms to it. But the things that I was doing, I have that Cn that you saw earlier, the 160 sine of m pi over 2, and then divided by the pi squared and the m squared here. And I have the sine in there as well. Now, the problem that I have is that I couldn't type all this stuff on this single line. So I went ahead and called this term. And then the next part of it, I said, take the term and multiply it by the exponential there. Okay, exp for e to the power. And that there has the minus m squared and so forth in it. And then I told it to go ahead and add the term into the s values, and then to go ahead and plot that. As you'll notice, that says that it's plotting with the K. K means we're plotting in black, and black is the tent shape that we have up at the top. So then I came back down here, and when I did this initially, I came along and did just one at a time. But after I figured out how to do it, then I put it into a loop. So what I'm going to do here is to take and let my t values evolve. So I needed to store those temporarily into something. You could call it whatever you want. I called it temp. And I say np.a range of 5. And that's going to go 0, 1, 2, 3, 4. Remember, it doesn't do 5 and it doesn't start at 1. Okay. So then I said my t value that appeared elsewhere is going to be 50 times the temp plus 1. If you're wondering, gosh, why did he use 50? I experimented around and 50 made the little curves that you saw in there a little bit farther apart was all. Okay. So then I started my S to be 0. And then I came along and did the same thing about the terms as I did before. But now the t that appears right here will have a value other than 0. And so when I add those up and get my new S, I tell it to plot. Now notice that the plt.plot is inside of this for loop here. Because it is inside of the for loop, that means it's going to get repeated over and over again. Okay. Also, I did not tell it what color to make that. If you want to go ahead and specify color, it's fine. But if you don't specify a color, it will choose a new color each time. So also another little awkward thing that I found out is whatever is the most recent curve that it drew, that will always be the one that's on top. So anyway, then my last thing there, we can see what's happening on this curve, that as time is going forward, this is going to collapse down towards 0. So I just drew that little dotted line there by saying use the x values and then put zeros everywhere that, an x corresponds. And then I told it to make it K for black, B was taken, so for blue, and so they use K for black, and then the dash dash means that it's going to make a dash line. So there's several little patterns like that. If you say dot, it will make a great big globby dot on there. It's kind of hard to read, but if you go dash dot, you can get different lines. So anyway, I am going to go ahead and stop there and fix my notes a little bit and upload things. For the work y'all are doing, I'm just going to ask you to do like a couple of these. They are cumbersome, because you have to do all this integrating. And if you do it by hand, you're going to make a mistake. And if you do it on the computer and you read it off the computer, you read it off Symbolab or Wolfram Alpha or whatever you're doing, you're going to copy it wrong. I'm sorry. So you need lots of time. You need to not do a whole bunch of examples. It's just kind of chugging through and seeing what happens with it. Okay. So we're looking at heat diffusion examples. I'll ask you to do like 2 or 3 of them. That'll be it, and you'll get it figured out. All right. See y'all tomorrow.